There, okay. Soon I'm going to be posting the details on like the lecture that you're all going to give. I'll give like a list of like suggested topics, but don't feel as if that should restrict you. You should feel free to decide what you want to do. Just check with me first. I haven't figured it all out yet. I'll have a date by when everyone needs to have a topic picked. And we'll also have to start setting the schedule. I figure the lectures are going to have to start happening at like the end of this month. Right? And each lecture will be about like 20 minutes, I would say. Each person will have 20 minutes, and I think there's 11 people in the class, so we'll do 2 a day, so it'll go on a little bit. But also, I want to make sure there's enough time at the end of the semester because for the final project, where I think I'm going to have it so you could probably work in like, if you want, you can work in like a group of 2, but you don't have to. You'll have a choice to do a final report like you do for the assignments, or you could give another lecture on what you did. Basically, it would follow the same idea as a report, but it would be more like the website stuff. So you would just kind of like walk us through what you did and why it worked, why it didn't work, what was interesting, what wasn't interesting, etc. So for some reason, I think people are going to be more inclined to do like the lecture for their final project as opposed to the report, but it's entirely up to everybody. I could be wrong.
So for the topic of the final lecture, like it's have to relate to
Yeah, and I'm going to be very flexible, right? So I want interesting stuff. Yeah. Anyways, any questions about any of that? Yeah.
Not specifically about the final project, but the reports for the assignments in general. Is there a page length min and max?
Try not to make it more than 8 pages if you do the double column. There's really no minimum other than, there's a maximum. Don't make it big. Markers don't want to read shit, okay? I hate to say it. But there's no minimum, but if it's insufficient, it's insufficient, right? So use your best judgment. Marker will be nice, I think, so. Yeah. Other questions? All right. Okay, so this is basically where we left off, right? We were talking, like, realistically, you don't want to use evolutionary computation if you don't have to. And this goes along with a lot of other heavy-duty algorithms. You don't want to use them if you don't have to, but at the end of the day, there are a lot of problems out there where there are no tractable solutions. At least we don't know of any yet. And a lot of times, finding the best solution is still, it's a pipe dream. We don't even bother with it. Really what we just want is a good solution that's, it'll address the problem. With this stuff, sometimes when all else fails, yeah, you throw an evolutionary algorithm at it and you hope for the best. Maybe you throw deep learning at your problem, you hope for the best. One neat thing about evolutionary computation is like, because it's population-based, like, when you're, like, raise your hand if you've got, like, the TSP implementation working. Okay, 2, 3, 4, 5, the half person, yeah. Obviously, at the end, you've got a population. Like, what were your population sizes? Like 100, 200, 1,000, whatever. You look for the best one in that population, and you go, yay. But you've got a population of good solutions. Some are going to be terrible as a consequence of mutation on the last iteration, kind of messing things up. But when you look at the average fitness of the population, you actually have a suite of solutions, which is kind of nice, right? It's actually kind of nice to have options, even if the one you pick that has the best fitness, maybe there's something about it you don't like. So you just look at the population and you find another one that you do like that's also got a good enough solution. So that's kind of nice. Evolutionary computations, one thing that's really nice about it is it tends to work well. Now this won't make a lot of sense for like TSP, but in real world data, like when you're solving real world problems, you have noisy data. You never have nice, clean data. Data is noisy, it's garbage, it's trash. And evolutionary computation tends to work really well with noisy data. It works well in non-continuous search spaces as well. There's forms of evolutionary computation where you don't even need a gradient and it'll still work. And really, the thing I like the most about it is there exists really good TSP solvers. There's algorithms out there that are really good at finding solutions to TSP. And the amount of expertise and knowledge and skill you have to develop that algorithm, you need to be someone special, right? And you need to have dedicated a lot of time to thinking about it. But let's be honest, how long would you say it took you to get like a working implementation for TSP of the GA?
Hour?
An hour? What about you? You know, an hour, maybe 2, 3, whatever, a couple hours, let's say. Yeah, you can get a damn good solution. Maybe there's a heuristic out there that someone dedicated a year and a half of their life coming up with the best TSP solver. Yeah, they're going to get a better solution than you. But you were able to get a damn good solution in an hour or two. So one nice thing about evolutionary computation is I don't actually even need to know a lot about the problem in order to get good solutions for it. And so we've got this little graphic here. Imagine we could do a random search for any problem, and it's not going to be very good. We can do evolutionary computation, and it'll probably do better than, hopefully it's going to do better than a random search. But it's never going to beat out something that someone has like a very special, tailor-made algorithm for a problem. It's never going to beat that. But it's always like, you know, a give and take. It took an hour and a bit to get a working GA for TSP. It took this person years to get their TSP solver. I don't know. I'm really lazy. I like the EA. I like the evolutionary algorithm here. Cool. Now, you don't need to be an expert on TSP to use that person's really good TSP solver. So if there exists a special tailor-made, really good quality algorithm to solve a problem, use it. If you're all out of ideas, throw a GA at it. Hope for the best. That's the world we're in. I think I was at the end of the previous, or maybe even 2 ago, I said, I think it was around the origin topic, I asked people to, you know, just spend time thinking about how systems that you can observe in your day-to-day life kind of came to be. Like, did anyone actually spend time doing that yet? No? That's too bad. All right. That's a shame. Okay, representation. Obviously, we're aware of what representation is. But this is going to be a topic going into digging a little bit more into representations. So for a given problem, we need to be able to encode it somehow in the computer. Sometimes it's obvious. Sometimes it's not obvious. Sometimes there is an obvious encoding, but then there's also a clever encoding that's less obvious but better. It's hard to say. But at the end of the day, we got to encode it somehow in our computer. And when we have a problem, and we want to use an evolutionary algorithm for it, one of the first things we need to think about is, well, how am I going to represent it? I need to know how I'm going to do that. So if you were working on TSP, one of the first things you probably did was, yeah, what should the encoding actually be? And I noticed a bunch of people already, they concluded they should use that permutation encoding, not just an arbitrary list of numbers where it's not a permutation where you could visit the same city twice, right? So obviously you spent some time thinking about it, and that's a good thing. We can encode problems however we want, as long as we have a system for decoding the encoded candidate solution. But the choice of how we encode things is going to impact the quality of our evolutionary algorithm. And very broadly speaking, here's like a collection of some, I don't know why the permutation is lowercase. Someone can make a pull request and fix that. If they don't do it quickly, I will, though. Here's a list of some common encodings that you're going to see. This is not exhaustive, but these are ones that you see. There's a binary encoding. This is actually like the early, if you go back to the ancient times of genetic algorithms, binary encodings were used for everything. Because really, you could represent anything in binary. You just need a decoding process to decode it. And there's actually some interesting properties that we can take advantage of with binary encodings. But the reality is they're not really popular. Even though there's some nice properties about them, the added overhead of like how complex it is to encode and decode things into a binary encoding isn't really worth it a lot of times. We have just integer encodings. Maybe it's a string of integers, right? Some list of integers that means something. It could get decoded, I don't know. Real value, floating point numbers. Maybe we're evolving weights of an artificial neural network, right? Each index in my array corresponds to one edge's weight in the neural network, and the value in that index is that edge's weight. I don't know, could be whatever. Permutations, like for TSP, that's a good one to use. So it's like integers, although it doesn't need to be integers. But if we have integers, we just create permutations of those integers. There's tree structure representations. This really comes up with with genetic programming, and then you can actually even encode finite state machines. That's like I think evolutionary strategies, but I might have that wrong. And really, we can encode whatever we want, however we want, as long as we have a good encoding and decoding process. How do we go from the phenotype space to the genotype space and back? Sometimes that encoding and decoding process is trivial. The bit string example, that was pretty trivial. Sometimes we got to do a little extra work in order to take what the encoding means to the phenotype. Certain forms of evolutionary algorithms are designed with certain types of encodings in mind, like genetic programming uses tree structures almost always, typically. Maybe I should say typically. But if it's not clear at this point in the semester, everything we've seen so far is such a high-level framework that you can do whatever the hell you want. So there's really, the rules that there aren't even really hard and fast rules. As previously discussed, the phenotype is a solution to the problem, and the genotype is an encoded solution to a problem. So here's, maybe my phenotype space is, like if we have that binary number 1, we have an integer. And we encode it, in the genotype space, it's encoded as its binary value. So the encoding and decoding there's a bit of a process there. You have to convert it to the binary and back, but it's not too crazy. This isn't that direct of an encoding. People might argue this is a bit of what we would say like an indirect encoding. But this is a very relative term. Some people try to use these as very absolute terms, but no, these are relative terms. For TSP, if you used a permutation representation, which represents the order that you visit the cities, that's a very direct encoding. It's the order you visit the cities. Do you need a Hamiltonian cycle? What is that? Well, that can be defined by the ordered list of cities that you visit in order. So if the encoding is just a list of cities in order, that's a very direct encoding. But these are relative terms. Some things are direct. Some things are more direct than others. Some things are less direct. They're more indirect, et cetera, right? That's it. The choice of representation will have a big impact on the performance of the evolutionary algorithm. I already said this. The difference between solutions in the phenotype space can differ from the difference in the genotype space. So if you consider that unsigned binary number maximization problem, the number 7 and the number 8. In the phenotype space, they're adjacent. 7 and 8 are next to each other, right? They are adjacent. They're right next to each other. But in the genotype space, they're actually pretty far apart. I mean, if we think of like a Hamming distance, how many of these things need to change to get from 0, 1, 1, 1 to 1, 0, 0, 0? 4 things. I have to take 4 steps. So I've got to, and so here's an example of Hamming distance with only 3 bits. So you can kind of visualize the difference, the distance. With the integer space, we have a one-dimensional space, right? 7 is next to 8, and 9 is next to 8. But nothing else is next to 8. What's interesting in the binary space, and this is with only 3 bits, is the topology of that space is very different. It's not one-dimensional anymore. Look at this. We've got multiple dimensions we can go in. We can go, if we change, like there are 3 numbers adjacent to 0, 0, 0 in that binary space, right? This one is 1 away, 0, 0, 1, 0, 1, 0, and 1, 0, 0 is all 1 unit of distance away if we were considering Hamming distance in the genotype space. And that's with 3 bits. If we add a 4th bit, we add another dimension. Point being, the phenotype and genotype, the shape of their spaces can be wildly different, and that could be taken advantage of. That could be something very powerful. TSP. If we did, we already talked about this, I think last class, if not last, the previous one. If we used an integer encoding for TSP, given n cities, assign each city a unique integer, an ordered list of n integers would define a cycle. The last city at index n would return to the first city at index 0. Since the ordered list has a total of n indices and the number of possible integers, cities that could exist in each index is n, the search space has a size of n to the n. But this particular encoding isn't great because so the first thing you have to ask is, does this encoding contain all possible valid solutions? And the answer is yes, it does. But it also contains a hell of a lot of invalid solutions. Those where you keep visiting the same city multiple times and never get to the city number 2 for whatever reason. So this integer encoding is sufficient, but it comes with a lot of extra. That space is really big, and bigger spaces are harder to search through. So if we can come up with a better encoding, maybe we can reduce the search space. Well, this is where the permutation encoding comes in. Now, instead of having n indices with n possible cities, n possible integers in each one, now I have n indices where I have n possible integers in each one, or at least in index 0, but once I pick one, I only have n minus 1 that I could visit after I am at a city. If I go to one city, I have one less city I could go to. So it's n times n minus 1 times n minus 2 times n minus 3. So this is where that factorial comes in. I'll just read it again just in case. All right, this would ensure that each exists. Yeah. Since the ordered list has a total of n indices and the number of cities available for index 0 is n, index 1 is n minus 1, index 2 is n minus 2, etc., the search space is n factorial. But in the above figure, consider the following ordered lists: 0, 3, 5, 2, 4, 1, and 2, 4, 1, 0, 3, 5. This is the same Hamiltonian cycle. And this actually was asked by, I forget his name right now, but he's not here today. This was asked by the guy that was sitting there last time, does it really matter which city you start at? Because really, all that really matters, like if I have a cycle, right, I could say I started here or here or here. It's kind of arbitrary. It doesn't really matter. And that's right. But if we don't fix the starting city, these two are both valid, right? But they're identical. If we fixed the starting city to always be like city 0, for whatever reason, maybe we say index 0 always has to be city 0, or maybe you decide I'm not even going to include city 0 in assuming that's the city I want to start at. I'm not even going to include that in my encoding. I'm just always, whenever I calculate the fitness, I'm always going to start at 0, calculate the distance from 0 to whatever's at index 1, and then whatever's at the last index to index 0. I mean, it's up to you. Do whatever the hell you want. But if I fix the starting city, I eliminate every possible rotation of the same permutation, where a rotation is just like, okay, right? So this is like rotated 1, 2, 3 indices, this particular example. But there's a lot more that are the same Hamiltonian cycle. It's just a rotation of the same permutation. Does this make sense? I'm seeing a lot of blank faces, which is hard to tell if you're like, this is boring, I know it's obvious, or if you're confused as hell. I'm seeing thumbs up, so I'll assume I assume you speak for everybody, so okay. Both permutations define the same Hamiltonian cycle. Yeah. So this means that now, if we fix the starting city, we actually don't have n factorial anymore. We have n minus 1 factorial. So the search space is a little bit smaller now. N to the n is terrible. N to the n sucks. That's big. N factorial, it still sucks, don't get me wrong, but it's less than this. That's good. And n minus 1 factorial, it's still horrible. Don't get me wrong, this still sucks really bad. But it's an improvement, and if we can reduce the search space, do it. This will still include, we are being very thoughtful and careful about our encoding, because we're being careful to not exclude valid solutions. We are just reducing the search space without eliminating valid solutions. Sure, we eliminated the rotations, which are valid solutions, but they're redundant. They really don't add anything, right? Now, what's the smallest the search space could actually be while still encoding all valid solutions? There may or may not be a gap in what I have as my encoding and what I could, like how small the representation could be to encode everything. There may or may not be a gap. I might be aware of that gap, or I might not even be aware of that gap, but it could be there. For example, here's the following. Look at these two ordered lists. They're true permutations. But what do you notice about them? They're the same, but reverse. One goes 0, 3, 5, 2, 4, 1. 0, 3, 5, 2, 4, 1. And the other one goes 0, 1, 4, 2, 5, 3. It's the same. Sure, we did it in a different order, and maybe that's meaningful for me, but I'm not thinking it's too important here for my encoding for TSP. If I could find out a way to eliminate the reversals, how do I do that? Well, if I could find out a way to eliminate the reversed ones from my encoding, I would even have n minus 1 factorial divided by 2. which is even smaller. But how can I do that? How can I ensure my encoding doesn't contain the reverse order? Like, is there something I can do? I don't know. I can't think of anything right now. But clearly, we could make the search space smaller. But with the way I've thought of my encoding, I haven't actually been able to half it. Maybe there's a clever way to do it. I don't know. I haven't thought of it. But that would be an example of the gap here. It could be literally half the size if I could come up with a way to eliminate the reversed order. I don't know. Is that clear? Yeah. Okay. N queens. Raise your hand if you've heard of this problem before. So here's the problem. You have an n by n chessboard. Let's stick with 8 by 8 chessboard, 8 queens. You have an n by n chessboard, or here, actually this one is a 10 by 10 example. The goal is place n queens, here place 10 queens on the chessboard such that they can't attack each other. They're all safe. So let's check it out. This queen, okay, nothing there, and nothing along that diagonal. That one's good. Nothing in the rows, columns, diagonal. No, looks good. Nothing rows, column, diagonals. This one is a valid configuration. This configuration of queens, this one is actually called like a staircase solution. They have a special name for it. But that is a valid solution. But, you know, there's more. So if I tell you, I want you to find a configuration of the chessboard for 20 queens, let's say, a 20 queens problem. Can you find that configuration, right? This is what I want. Is the problem clear? So how could we encode this? Well, to me, the most obvious potential encoding is, why don't I just have like a 2D list? A 2D n by n list that represents effectively the board, right? Yeah? Then n cells in that list will be filled, let's say. So the idea is I just have an n by n, right? The idea is of all these cells, n will be filled. I don't know, one there, one there, one there, and so on, right? Maybe it's zeros and ones. Maybe it's a 2D binary encoding, whatever. 0, it's empty. 1, that's something there. So this is what I would call a very direct representation. The encoding and what it means are very connected. They're very similar. I have a 2D list. I have a list of lists representing the encoding. So how big is that search space? Well, that would be n by n, choose 8, right? Order doesn't matter. So for 8 queens, that's 64. Choose 8, that's 4,426,368. My goodness, I can't say integers today. Oof. So we're not off to a good start today. Oof. So that's how many there are. I mean, that's not that bad, right? But we always want to ask that question. Well, first of all, that's 8 by 8. I don't know, what's 10 by 10? What's 100? Okay, this is going to grow pretty fast, pretty quickly, it looks like. What's Yeah, this is growing pretty quickly. Let's say 20 by 20, choose 20. Let's add parentheses so it doesn't get confused. Yeah, this is going to grow pretty big. Okay, all right. Well, we always want to play this game of how small can we make it? This search space, first and foremost, does this encoding represent all possible valid board configurations? Yes, it does. But it also includes a lot of potential invalid board, or not invalid, but maybe inadmissible solutions is a better word. Everything's a potential solution, but it's not, some aren't going to be great. For example, you know, like here, right? See in my example right here, maybe you can't see. Let me do this real slowly. Right, we've got two right on top of each other, right? So, although that's a valid board configuration, we know that's not going to be like a correct solution to n queens because they're in the same column. So that's no good. So let's try again. Let's come up with like a 1D list of coordinates. (2D) encodings are also tricky to work with. Like when you look at that, if you think you had a list of lists, how would you do crossover? How would you do mutation? You could come up with some, right? But it's not necessarily immediately obvious, at least what we're used to with the one-dimensional lists. So perhaps we could do a 1D list of xy coordinates. It would require a list of size n, right? Each index corresponds to one queen, and the value in there is like an xy coordinate. I mean, we're just thinking of potential encodings at this point. XY would be like row, column, okay? Or maybe column, row. The representation it's a little less direct than the 2D list, but it's still not hard to get to what it means. It's a coordinate system, right? So instead of the 2D one where it's a very clear, direct representation, now it's a little less direct, but it's not too bad. So for each, there are n queens that need to be placed. Each queen has an xy coordinate, and there are n times n possible positions for each queen. So I have to have an xy coordinate for each of the n indices in my list. Well, that's how many possible xy coordinates are there? Well, that's n times n. And I have to have n of those. So n times n to the power of n. Whew. So for 8 queens, that's actually 64 to the power of 8. That's 10 to the 14. This encoding is actually worse than the 2D one. Who can tell me why it's worse? Like, how did we get to a worse encoding in terms of the size of the search space? Yeah, we could be putting n queens on the same square, right? They could all be at 0, 0. Where the other encoding, this one, we never had that as an option. It was never possible to put a queen in the same cell, right? So this xy coordinate, obviously we've got a bit of an issue there. Okay, so let's try again. Queens are not to attack one another, are not to be able to attack one another. They can't be in the same row or column, right? If they're in the same column, that's a problem. If they're in the same row, that's a problem. So each column can only have one queen in it, right? Would you agree? For at least for a solution to be valid, each column can only have one queen in it. So let's have a list of size n. The index in the list will correspond to the column, and the value at that index will correspond to the row. Does this make sense now? So if I had this index 0 would be 0. Maybe there was a, I don't know, maybe there was an x down here. Index 1 would have 0, 1, 2, 3, and so on. So now the index of the list corresponds to the column, and the integer corresponds to the row that the queen is in. But we could take this a step further. Let's make it a permutation. If each index corresponds to an individual column, it's not possible to have any column contain more than one queen, right? Because there's only one value you can put into each index. If we have a permutation, that means the value at each index must be unique. Meaning, if the values are unique, no two queens could be in the same row. Right? Take a moment. See if I have an image. So this here, let me make sure I didn't miss anything. Use permutation, this would, yeah, okay, this would ensure, okay, in other words, with a permutation encoding, each queen must be in a different column as the columns are defined by the index of the list, and each queen must be in a different row since the rows are defined by the values in the list, which are unique because it's a permutation. So this configuration here, with this type of encoding, would be 2, 5, 7, 0, 4, 6, 1, 3. 2, 5, I guess the numbering I have is, ignore the numbering on the side because that's not relevant for the encoding. 7, 0, 4, 6, 1, 3. Right? Now, how big is this search space? Well, it's a permutation. This is going to be n factorial, right? How many possible values can be at index 0? N. Once one value is picked, how many can be in the next one? N minus 1, n minus 2, n minus 3. So the total number of possible, the search space size is n factorial. Where with 8, look, n factorial, that's not good, but it's an improvement. And with 8, it's actually only 40,000. So if we go back to the 2D encoding, which was 4 billion, now we're down to 40,000. That is 1, 2, 3, 4, 5 orders of magnitude smaller. That's good. That's very good. But I want to be very clear. This example, it includes all possible, this encoding includes all possible valid configurations, and it excludes a lot of inadmissible configurations, which is a good thing. We haven't eliminated anything that could be correct. We've eliminated a lot of things that would be incorrect. This is awesome. There might be a gap. There might be a way I could ensure that this is, there might be a way that I could ensure that everything is valid with an even smaller search space. I don't know. but this is pretty good. But let's be honest. This is not a very direct encoding. The 2D lists, that was direct. The 1D list was less direct, but not too bad. This type of encoding, this permutation encoding, we got some decoding to do to make sense of what this actually means. It's not crazy, but to go from a permutation of length n to what it means for a chessboard, we need to write an algorithm to do that decoding. Be honest. Was this an obvious encoding? Like, I walked you through this, but be honest, would you have thought of this encoding? I don't think so. Maybe you would have if I gave you a lot of time to think about it. Maybe. But this is not an immediately obvious encoding. But clearly we can see this is a damn good encoding to use for this problem, because look how small the search space is. We reduced it by an order of like 5 orders of magnitude. That's really good, right? Now, everything we've looked at so far are toy problems. When I say toy problem, I don't mean it's useless. I don't mean it's trivial. I don't mean it's not interesting. What I mean is these are problems. These are like standard problems that we like to talk about. And the reason we like these ones is because they're well understood problems. They're intractable. Don't get me wrong. They're hard. But they're well understood. And when things are well understood, it allows us to make these, it allows us to reason about them a little easier. When you find a real world problem, if I tell you, okay, find an encoding for using a GA to teach a robot to walk. I don't know. I wouldn't recommend that, but let's say that's what you had to do. And you need to think of your encoding. And you're going to want to start to eliminate inadmissible configurations. What does that mean? Once you start looking at these actual problems, like these actual difficult problems that you would use evolutionary computation for, it's not always going to be easy to reason about how you can reduce the search space with a clever representation. That doesn't mean you shouldn't try. It just means that if walking through this, you're like, yeah, this isn't so bad. I can see how we reason through this. In practice, good luck. Real problems aren't nicely and cleanly and well understood like things like TSP and n-queens, right? Does that make sense? Yeah. So here's some examples. Okay, binary representation, there you go. Collection of zeros and ones. We use this for maximization of an unsigned binary number. Usually a very indirect encoding because, I mean, you could represent anything with binary. You could represent anything any way you want. You just, again, need that mechanism to encode, decode. You have an integer representation. It could be any integer or integer taken from some predefined set of integers. So you could have a list of integers, any representable integer in Python. Or maybe you only allow the integers 0, 1, 2, 3, 4 because 0, 1, 2, 3, 4 mean like north, south, east, and west for like a robot traversing a maze or something. It depends on what you were doing. The ordering of the integers that you're using may not matter. This is an important thing to note. The fact that 0 is less than 1 might be meaningful for your problem, or it might be entirely irrelevant. 0 comes before 1, but north really, like, if 0 means north and 1 means south, there really isn't an ordering there, right? It was just an arbitrary label we assigned to north and south. So sometimes the integers that you're using for the encoding have meaning, sometimes they don't. In the order they have meaning, sometimes they don't. The order of the elements in the collection may or may not matter. This is, again, going to depend on what the problem is and what you're doing. But just be aware that really it's do whatever you want. The fact that one value comes at index 7 and another one at index 8, the fact that 7 comes before 8, Maybe that's important, maybe it's not. Whatever. It's a problem programming a robot. Yeah, the robot takes 10 steps. Yeah, okay. Permutation representation. An ordered of something from a set, multi-set. Multi-set's just a fancy word for a set where you can have multiple values, multiple repeated values in it, just FYI. It's just an arrangement of values in some sequence, useful in situations where each value should be unique, like TSP, or the n-queens problem that we saw. It doesn't need to be numerical, though. And the order of the elements in the chromosome matters. With the permutation, the order matters. That's kind of like the whole point of the permutation. So I could, maybe I wanted to have maybe I gave you the problem. Consider the problem of finding English words from a given multi-set of letters. And I give you this multi-set of letters. There you go. There's a below possible chromosomes, right? There you go. And then real value representations. Collection of real or floating point numbers. Of course, computers suck with real numbers, so we have floating point numbers that they also suck with. Consider the problem of encoding the weights of an artificial neural network or finding the xy coordinate in some complex function where you're looking for the minimum value of some function, right? So you're looking for real, we can operate in real numbers, whatever. This is actually called the Ackley function. It's kind of a famous problem for real number optimization. Certain forms of evolutionary computation are designed with real numbers in mind. GAs, although they can work with real numbers, they're not really known for being good at working with real numbers. Tree representations. This is often what you see with genetic programming. They can be used to encode programs or functions. So the tree on the left means 1.2 minus x times y. The one in the middle, that's some Boolean expression. If the length is less than 5.2 or the thing is not read, right? Some Boolean expression. And here we actually have some operation, a little bit more complex. There's an if. If the door is open and the right door is closed, move forward, otherwise turn right. I don't know. These are arbitrary. They're made up. They don't really matter. But this is how you can use a tree to encode functions. These are called S expressions, symbolic expressions. Anyways, that's that. Any questions? Yes?
For the queen problem?
Yeah.
Can we add the limit of no queen diagonally?
So if you can find out how to do that in a clever way, as an enforcement for your representation, do it. But if you can't, but tell me what that is, right? So the permutation representation intrinsically eliminates the rows and columns being an issue. But what can we do to that representation to ultimately eliminate anything in the diagonals? Because if we could, we've solved the problem, right? Yeah. But you could argue that's the gap. If you find that gap, though, I'm pretty sure you've solved the problem. If you have an encoding where it's impossible for queens to be in the same rows or columns and diagonals, well, that's just a set of possible solutions then. So find that and win $1 million, I'm guessing. Yeah.
For the queen problem, the gap would be rotational and functional.
Yeah. Well, would it though? Because, would it? I don't know. Actually, this is a good question, and unfortunately, we don't really have time to really sink our teeth into it, but this is a fun one because we are bound by the end of the board. So if I rotated it, will that matter? Let's revisit this when we do have class. What day? Today's Wednesday, right? Yeah. Let's talk about this Friday. Yeah. That could be fun. Anyways, any other last questions, thoughts, concerns, whatever? All right, cool.